Okay, ladies and gentlemen, welcome to this lecture on robotics, sponsored by Lockheed Martin. Today is a happy day for me because it's not every day that I have the good chance or the privilege to introduce to you such an amazing guy as Henrik Christensen. I met Henrik about 30 years ago when he was a graduate student at the University of Aalborg, and I was an assistant professor here at the University of Maryland. And his lab was participating in a European project called VAP, Vision as a Process. And they invited a few universities from the US, University of Maryland, Pennsylvania, UMass,
and Rochester.
And we spent a lot of time together having meetings every year. I recall we had a meeting once in a monastery in Sweden. And the monks had given us a room called Rock Room, which means smoking room. And Henrik and I went to that room smoking. And the whole workshop came inside that room. It was amazing.
It was amazing. You couldn't see each other in the room, but...
There was a cloud of smoke in a small room with everybody there. Well, after Henrik finished his PhD, he did very interesting work on aspect graphs. He became a professor at the Royal Institute of Technology in Sweden. And he started a very interesting research program where he was doing active perception and robotics. And he had basically started what is known today as AI and robotics. But while he was there, Henrik convinced the European Union to fund at $1 billion level a new program on cognitive robotics. And he was very successful. There was a tremendous number of projects that started in Europe and a lot of interesting work that happened. So Europe was too small for Henrik. And so, like all young men, he went west. And he came to America, where he became a professor at Georgia Tech and a director of a robotics institute there. And while he was there, he got together with a number of presidents from universities, and he went to Congress. And he convinced the congressmen to start a new program called the National Robotics Initiative, or NRI, that has already given perhaps $1 billion in
700
from the National Science Foundation, and almost every other roboticist in this country has been supported by this program. So after that, Henrik moved to the town with the best weather in this country, San Diego, and he is now a professor at the University of California, San Diego, and the director of the Robotics Institute there. And today, he is going to talk to us about deploying
autonomous cars, right,
in the campus and all the interrelated problems of navigation and AI.
Thank you, Yanis. Well, first of all, great to see you all, and thank you for inviting me. I haven't been out to give sort of in-person lectures for 18 months, and it gets boring looking at 25 icons. So I'm very ready to talk to people about this. What I wanted to talk to you about today, or give you sort of an overview of, is a program of how do we build autonomous driving vehicles that can drive on campus. And I'll give you a little bit of background. But first I should sort of say, even though I'm talking about it, this really involves a lot of other people. So if you don't like it, blame me. If you like it, you should give them the credit. So that's sort of the credit assignment problem. I take negative feedback, they take positive feedback. So autonomous driving cars. There's a lot of hype about autonomous driving cars. It's not really a new problem. This is the front page of Scientific American from 1916, where they said, soon we'll have autonomous driving cars. That was 105 years ago. So they said, soon, as soon as we get electrical cars, these will all be autonomous driving cars. And still, every day we sort of hear in the newspapers about soon we'll get autonomous driving cars. If we still sort of stay in the history, then sort of 125 years ago, we saw sort of this revolution from horse carriages to automotives. So over a relatively short period of time, we saw this. So the question is, have we made progress? Well, 1916, so about 100 years ago, 105 years ago, the speed of horse carriages in London was 17 miles an hour. Today, automotive traffic moves in London at 12 miles an hour. So we've actually moved backwards. So I think it's sort of important to keep in mind that you might have a level 5 autonomous driving car. Once you get on I-95, because there's a lot of other drivers there, you might have the smartest car in the state and you're still not moving. So we need to sort of think about the systems problem of how do we actually solve autonomous driving cars where they can talk to each other, where they can do all of this. Because otherwise, 25 years from now, we're going to be at 10 miles an hour, which is even worse. So the question is, what can we do? So I was interested in that problem. And then I went and looked at sort of UCSD. The text is probably too small, but it doesn't really matter. We have about 35,000 students on campus. And we have sort of 35,000 staff and faculty. And we have 40,000 students on campus. So 75,000 show up on campus on a non-COVID day. And that poses sort of a huge challenge for how can we actually handle this. And there's a lot of, most autonomous driving cars today are driving on the interstates. It's a 1D navigation problem. You just have to make sure you stay on the road. If you go on a university campus, I've walked a little bit on UMD, but not enough to know if you are like UCSD. But on UCSD, the students consider themselves that they own campus. They can walk wherever they like, and you just have to adapt to it. So the burden of not running into student is on the staff and the faculty and on the bus drivers. So they will just walk anywhere. So that's an interesting challenge. Can we build vehicles that can actually drive around in this environment? At the same time, there is a lot of opportunities to switch away from traditional cars. So in particular, younger people don't necessarily want to own a car because they have different car needs. If you are Wednesday evening, you're going for a grocery, give me the cheapest possible mean of get from A to B. If you are Saturday going to IKEA to buy new furniture for the dorm, you want, a truck, a U-Haul or something like that. Saturday night, you're going out on a date, I want a Ferrari. So the question is, most of us cannot afford a U-Haul, a Ferrari, and a dumpster. So the question is, what can we do? We do drive services instead. So that kind of sort of service economy really comes in. So at the UCSD, we've looked at, there's lots of places where we do pickups, so we've analyzed sort of statistics. Now the question is, could I build a vehicle that could actually operate in this environment? So we wanted to sort of use the campus as a laboratory for studying autonomous driving cars. And of course, I come from Europe, as Yannis already told you about. In Europe, you have one police that sort of controls the country and everything that sort of happens. In the US, every institution has its own police. So as long as I can agree with the chief of police at UCSD that we're going to change the traffic laws for autonomous driving cars, we're good to go. So that makes my life a lot easier that, I can drive autonomous driving cars on campus as long as the police chief says it's okay. I don't have to worry about the California rules or everybody else. So that makes my life easier. Now I just had to figure out what can I do. So what I was interested in was not to do traditional highway driving. I wanted to do urban driving. I want to do it in a place where there's a lot of pedestrians. So how do I model all of these pedestrians? I want to do it in an environment that is very dynamic. So if I go out, I don't know what your campus is. UCSD is an 8-crane campus. So the Chancellor is very proud. We have 8 buildings being constructed right now. And I was here 2-3 years ago for a workshop that Yannis organized. That was before the CS building was there at the entrance. And I've already seen 5 or 6 different buildings. So the problem is, if I go out and I build a map of campus, it's typically going to be invalid. If you're lucky, in a month. If you're unlucky, tomorrow. So you can't sort of say, well, we'll just build a map of campus and then we'll use it. That doesn't work. So I was very interested in how can I sort of build sort of a perception action loop at the bottom? How can I integrate it in with traffic devices, with communication? How can I think about fleet management? How can I think about all of this? And at the same time, make it accessible to humans. There's lots of people that work on each of those blue boxes. But there's basically nobody that works on how do I actually put it all together. So I was more interested in how can I actually put all of this together. And, like, how hard can it be? So, so we bought, a couple of golf carts, brought in some students. It's not hard to get students for autonomous driving. They all get jobs that pay twice my salary afterwards. So they're all lining up and said, give me a job, and then I'll go and get it. So I always have a line of students lining up for this. So we built these golf carts, put some cameras on there, we have a lidar on there. We have a bunch of ultrasonics. So I fundamentally don't believe in lidar. I believe lidar is a sort of cheating. So if I could do it in vision, I want to get only to vision. But, we'll get there. And I'll talk you sort of through these. So it's a vehicle it's a GEM E6. It has 6 seats because it's basically a mobile lab. I can have 6 graduate students sitting on board and programming it while it drives around. Don't have them sit somewhere else, If you're not in the car, you're not risking your own. It's easy to sit somewhere else and say, well, we'll take a short turn here. If you're in the car, you're sort of committed, So we want to have this. So we did this. We have a lidar. We have 6 very good cameras. They've since been upgraded. The advantage today is that we're seeing tremendous progress. So because of cell phone technology, we're now at a point where we can do cameras with 140 dB dynamic range. That implies that I can drive on a sunny day out on I-95, and I can see what's happening in the shades under the bridge. And that opens up for I don't have to worry about, should I look in the shades? Should I look on the road? I have enough dynamic range that I can do all of this. We have a bunch of sort of park sensors. We have actually not a very powerful computer, but an okay computer, and then we have a GPU on board. And it's actually helpful not to sort of say, well, just buy another GPU. No, you should be able to do it on a reasonable amount of computing. So that was our go. Then one of the things that we didn't want to do is that there's lots of these autonomous driving cars today that use what I call HD maps. So it's a very, very detailed map. So you've done sort of SLAM to millimeter accuracy, and somebody has annotated it so that you can sort of see where all the lanes are and all of this. And I'm sort of like, yeah, that doesn't work. That's not scalable. Because the problem is that, first of all, it's not available for most of the world. So I can't send a car from, across the US. So I wanted actually a model like this for the UCSD campus. I said, can I get one of those maps? And they said, no, we've only done it for the Bay Area and for the highways. I said, give me a price. And I said, yeah, no matter how much money we have, you can't do it. I was like, okay, so this is bullshit. So I wanted something else. So I said, okay, so I want to figure out how can I do this. What we can do is that we have OpenStreet Maps, which is basically a graphical model of what the world looks like. So it's graphs. It'll sort of say where the roads are with minimal GPS waypoints. It'll say where the intersections are. But beyond this, it doesn't really have very much. So it's like, think about it as Google Maps if you take away the street view. So I said, that I can work with. That's sort of realistic to do. So we wanted to build a system like this where we can do very traditional robotic system. Can I do some localization? Once I know where I am, and I have sort of the vector map, which is OpenStreet Maps, I can come up with a global plan. How do I get from here to the entrance of campus, or how can I get from here to the sports arena? Then I have some perception that gives me situational awareness, and then I can come up with a motion plan, and I can execute it. So for localization, we started out relatively simple. We started out by building a large grid map to get started. Did sort of scan matching. I'll show it to you on the next slide, knowing that this was a bad strategy, but we wanted to sort of know, let's get started and figure out where the hard problems are. Then slowly we went to sort of a feature-based matching strategy where we did this, and then eventually what you'll see at sort of the end of this presentation, we went to sort of doing semantic maps where we actually understand where's the road, where's the sidewalk, where are the pedestrian crossings, because that gives us a lot of contextual knowledge that will make it much better for us to be able to do driving. So we started out to sort of basically doing scan matching. So what you're seeing here is that you're seeing an A is basically an integrated map. It's 3 by 3 miles, so relatively large map. First of all, you know, when you build one of those, you're sort of like, okay, so we're going to run out of memory. What are we going to do after that? So that was one of our challenges. We said, okay, let's try this. We built sort of the laser scanner so we can do scan matching. It's not bad, but it's far from perfect. Then slowly we got to where we can actually do recognition of objects, like the cars in a parking lot. We can match it up. Initially, we did this with a lidar-based map. We can recognize street signs, so we know if this is, do we have to stop, do we not have to stop? That's actually also available in OpenStreet Maps. So it'll tell you which one of the crossing lanes do you have to stop at to be able to do this. We then have this, it's not fantastic contrast, but you can sort of see that the solid lines that you're seeing are basically, let's see, I have a cursor here. So the lines you're seeing here is basically what's in OpenStreet Maps. And the same thing sort of over here, you can sort of see. So we use this to plan a path, standard graph-based sort of optimization. We're actually using an A star, so it's a relatively simple. Later on, we were using sort of a Kinedynamic Planning so that we take acceleration into account. So it's not enough just to be able to drive it, but you actually have to take curvature into account as well so that you know you can drive on this path. We build all of this into a system. Here's a set of container. Of course, it's containerized. This is all running in the robot operating system. And we can track people. So we do sort of standard people tracking. Do your favorite whatever detector. Here we used a YOLO. And then we used a Kalman filter to do tracking. It's actually good enough. I'll show you later on some hints for doing this. So here is, so I'm giving you, this was how we got started. Then I'll tell you about what's not working. And then I'll tell you about what did we do to fix it. So here is how we got started.
Hi, I'm Henrik I Christensen. I'm the director of the Contextual Robotics Institute here at UCSD, where we do autonomy, smart robots for all sorts of applications. Right here, you're seeing our automated mail delivery system. So the experiment we're trying to do here is to understand how can we use these vehicles for doing micro, sort of the last mile logistics. And it's interesting to try and test these in a campus environment where we have regular traffic, we have pedestrians, we have scooters. So this opens up a number of new challenges for autonomous vehicles. We bought a vehicle, it's retrofitted so that we can do autonomous driving. It has cameras, it has a lidar, and it has various other sensors on there. And we've then programmed it so that it would automatically know where it is. It will detect other things around it, like other vehicles and pedestrians. And then we've sort of developed the logic to enable it to participate in traffic, so it can stay on the road, it will stay behind another vehicle. When we get up to an intersection, it will read what other vehicles are at this intersection, whose turn is it, and then it will use this to drive through it. So it will drive just like a regular driver through traffic, except it's all done by a computer. So the technology we're using this is relatively straightforward. We're using LiDAR, we're doing pattern detection to be able to fit into cars. to be able to detect. And we're using sort of a combination of neural networks and traditional programming to be able to do the detection of all the things around us. Then we use sort of traditional programming and planning to figure out, given the current situation, how do we determine what should we do next. So we started this about a year ago to build these vehicles, doing the planning, and now over the summer we've started to do.
So this is sort of the, this shows you about American system. There had to be 2 people in that. You can only drive it on the campus initially to do early testing if there's a safety driver, because if I run down a student, I get fired. So I wanted to be there a little bit longer, so I had to have a safety driver in there. And we're not allowed to touch campus mail. So there had to be a guy that actually did the mail delivery. So that was one of the things we had to sort of work on through this sort of test. So we did the test for 6 months. So we literally ran it 5 days a week for 6 months. So I wanted to know the statistics, what happens, so I can run it on a good day, on a bad day. We wanted to sort of know what will it take. So we drove it in the morning, we drove it in the afternoon. And when we started during the summer, so we have, so the first one here is mean distance between interventions, which is about half a kilometer. And the mean time between interventions was about 2 minutes. That was sort of the early version of the system. Then in the fall, when students arrive, in the summer there's no students, so it's relatively easy to handle a university campus. You can see the intervention distance goes down significantly. Suddenly we have students on campus. And students don't, their default assumption is, you will stop for me. So they'll walk on the street and say, oh yeah, no, maybe not. And so we just had to be willing to accept the fact that can we do intent recognition well enough that we can understand what these people are doing. And for that reason, you can also see our intervention time went down to sort of 1.5 minutes for this. So the mean distance between interventions is how far do you drive on the road between interventions?
In a meter,
in meters. In meters. So it's basically half a kilometer or 400 meters on the road between interventions. So we plotted this and said, where are the interventions? It's not a uniform function. So the interventions here are the sort of an area here where we're crossing over. And a big problem was that people would be standing on the corner talking to each other. And once they've been sort of, after 5 seconds, they're probably not going to go. And we start turning, and then people say, oh, I should really walk here. I'm like, ah. So, so that was unfortunately what you had to do. The same here is an area where people park, and people are typically illegally parked. So that was one of our challenges that often, we would come in, but also we would have people that are sitting in their car and say, oh, I should get out now. And like, so that was hard. So we had here illegally parked cars. Here, people would be standing on these corners. The same up here where we're doing sort of a left turn. And here, basically, people would totally ignore us. Over here, if we're actually driving in a student dorm area, and the number of people were just unbelievable. So it's very clear, the problems are, can we get good enough intent recognition? Can we get better sort of modeling of cars? Again, intent recognition. Here, how do you drive in a cluttered area? I haven't been enough around campus here to sort of know if you sort of walk on a pedestrian walkway with the students coming between classes and stuff like that. Yep.
Clarify, do the pedestrians or other people around know that this vehicle is autonomous?
No. Well, so on the back of the car now, it says experimental vehicle, expect erratic driving, but only on the back. So we didn't want it to sort of say this is an autonomous vehicle. So we didn't have an orange beeper or something like that on it that would say that it's actually autonomous. The reason why we put on the back of the car experimental vehicle, expect erratic driving, was that I don't know how it is in Maryland, but in California, at a stop line, you have to stop for 3 seconds to stop and look around. In California, nobody stops for 3 seconds. You do sort of a California stop, you come down almost to a stop, and then you continue. So when we started actually following the law, the number of bodily gestures and shouts and honks at us, oh, is this idiot that actually stops at stop signs? So we had to put this on the back of it and said experimental vehicle. And then I said, yeah, okay, it's an experimental vehicle. It's sort of okay. So there was a lot of sort of social engineering involved in getting people. People don't follow the law. The same here. You know, when people saw that it was a golf cart, they said, oh, we can cross the crossing here because, you know, he's driving slow, so we can get in front of it. So we wanted to actually study what does it take for this to really understand what are the challenges if you're trying to do this. And so it was impossible for us to, it was important for us, so what we see on the graph is that we see this is sort of our planned trajectory, this is a crosswalk, and so we have two crosswalks here. When we see people in here at a certain footprint, then we'll basically make the assumption it's a pedestrian. And then we have a pedestrian model that would allow us to sort of predict, where we'll say, in general, we'll say it's very stochastic. We have lots of examples of people sort of walking almost to the other side of the road and said, oh, wait a minute, I forgot my phone. And then they turn around and go in the opposite direction. You know, it's like, really, people? But that happens, and if you're a car, you just have to be able to take that into account. We can recognize larger entities as a car, and we know they're, in most cases, non-holonomic. We know what their dynamics is, so we can build in these kinds of dynamic models. But also, there's a lot of sort of contextual awareness. Here are people that are sort of at the side of the road. They look at the autonomous vehicle and said, come on, you can go first. And I'm like, no, it's an autonomous driving car. It doesn't understand these kinds of gestures where you're sort of. So that was very important to actually understand that there's all of this dynamics going on that is very important. But it's also very important to understand that here is traffic work going on, sort of on the side here, and there's a stop sign. Unfortunately, they haven't covered up the stop sign. If you stop in the middle of that traffic area, everybody will scream at you. So there's all of this sort of contextual awareness to understand. Here's an example where there's a stop sign. You should ignore it because of the guy here with the slow sign. So it's all of this scene understanding that's incredibly important for you to actually be able to drive. So if you make the assumption you can just read the DMV manual and drive that way, you're going to be in trouble. So it's very important to really understand that we have all of these special cases where you need to be able to do this. So I want to talk about some of the challenges that we had to sort of solve to actually be able to do this. So the first one is a very mundane problem, which was calibration of cameras. How do I calibrate my cameras? So it turns out that there's actually a very simple solution to this. So the first one is that there's a lot of known structures in your environment that you can actually use, and they don't change. So the first one we did was, it turns out that all stop signs are actually controlled by a size. The DMV has specified what a stop sign looks like. And this is just the stop signs, if you look at it. All the red dots here are stop signs. So you cannot drive 200 meters and not see a stop sign. So we said, oh, but now if I add all the other traffic signs, turns out that I'm driving around in a forest of known geometries. And I can basically use this forest of known geometries because, there's thousands of stop sign detectors out there. There's thousands of traffic sign detectors out there. There's a standard sort of NIST test for recognizing traffic signs. So if you go in and you do this, you can actually do detection of all of these traffic signs. We know the geometry of them. I can find the contour points. I can do sort of standard line detection, which has been around since, 1965. And I can use this then to do line refinement, and I can find sub-pixel accuracy points on this, and I can use this to do standard calibration. And by doing this, you can drive around, because if you drive around, you drive over bumps and all sorts of things. We can actually do this. So we did sort of this and have now a standard system that basically runs continuously. And here's sort of a reference test where you can see how it converges over time. But you can run this on your car and it will do auto-calibration of your sensors. And you can now extend this to radar and lidar, because there's a lot of known structures out there that you can use. So that was actually very helpful for us. The other thing we did is that we actually built, I said I don't believe in lidar, so what do I do to replace a lidar? I just build a ridiculous stereo camera. So we built sort of a ridiculous stereo camera. This is a stereo camera with 32 sensors in it. So I can do trinocular stereo between pairs of cameras all the time. Turns out that you can get these today. So I live in San Diego, which is Qualcomm City. Qualcomm says that I can get a good quality camera for $1, and I can get the CPU power to process it for $9. We took the cameras, we threw away the CPU, and we did it in an FPGA. So with this, we can come up with a system where basically for $200, we can build sort of a 3D camera that is actually very good, and we can do sort of auto-calibration. So one of our PhD students, Dominique Meyer, has built this system where you actually see sort of how it should come up with. Why is it not coming up with the colors? It should come up in a minute. So basically, we can drive through this and get very high-density 3D reconstruction of the environment. Here it's just showing sort of where the corner points are, and the point in a minute you'll see the points are getting detected. We can do automatic detection of where are the epipolar lines, where are the objects that we can do tracking on. And today, Dominique has graduated, and he now has a company that sells this. He doesn't sell the 3D camera for cars. He actually sells it for inspection of US infrastructure. So you can use this for inspecting bridges and all sorts of things, but it's really sort of relatively compact. It does very dense. So what he does is he has a gigabit Ethernet that you plug in at the bottom, and then you get close to a gigabit of live data coming out with complete sort of 3D reconstruction. So that was one way of trying to get around this. The other way we did was actually to try and build better maps than what we had before, is that we took our car, we took an RGB image, did semantic segmentation. I don't have time to get into the semantic segmentation. I can give you a pointer to a paper. But where we will recognize where are the traffic markings, where are the road surface, where are the sidewalks, where's the sky, where is vegetation. And that provides very important contextual information for us to be able to understand where are the drivable surfaces, where will you typically find the pedestrians, where will you find other road users. And having that contextual information is incredibly important for decision-making on this. So we then have a local point map, which can either be from a lidar, but it could also be from the 3D camera I just showed you from Dominique. And then we do sort of semantic association, so I now come up with a semantic point cloud map. So I have a 3D set of point clouds with road surface, sidewalks, vegetation, cars going on, and I can now do 3D SLAM on this, and then I get sort of a local semantic map of what you're seeing, where basically, so I'm doing SLAM based on this to come up with a map, so I can do relatively long range. So for all practical purposes, think of it as hundreds of meters or 100 meters, where I can do this, and I can recognize dynamic objects on it, like, so you can see the car over here is basically the car that you're seeing here. It will do all of that kind of sort of segmentation, which is incredibly valuable. So I can come up with an example map. We compute these. This is for reference. In reality, we don't store the map. We throw it away, because our experience is that on a university campus, it changes from day to day. Literally, you know, it's sort of because then there's a new construction going on, there's a water pipe that's broken. So you can't make the assumption that you can build a map and then make a month later assume that it's still there. It's just not realistic. For the global mapping, we started out by using sort of what you're seeing with the blue lines here, which is OpenStreet Maps. This is a vector-based map that's available, mainly maintained in open source. And some of you must have way too much time on your hands, because it's updated every hour. So you know, people must drive home from campus and say, cool, you know, they have a new roadwork over here. I should put it into my map. And I'm like, really? You know, that's what you want to do? But it's very good. Thank you. You know, it really helps me that people are constantly updating this. So we've seen things that are in OpenStreet Maps an hour after it happened. So it's very good because it's such a compact representation. You don't have to do a new SLAM where you drive around with a sensor rig and all of this. You can actually get to it, so it's pretty close. So initially we did sort of traditional trajectory-based planning, where we did sort of a variant of a Kinedynamic planner. So we'll do traditional sort of precision-based planning, but then it will also include curvature information, so you take into account precision, speed, and acceleration, and that you can do sort of in a reasonable amount of time. And here we then have a set of different hypotheses. What are the different set of paths that you would have, which we take into account, for instance, if there is a car parked on the side of the road, you can choose sort of another and say, wait a minute, I saw one of those. So if I go back and say, if I now see one of those red things in here, in my map, I will choose another one of those vectors. So you're basically maintaining a set of hypotheses of how should I be driving through this environment. And let's see, here's a map. Here's a very small example where sort of the path, you can see this is sort of the curvature for the car. This is sort of shown in slow speed, sort of, I think it's a tenth of actual speed it's showing, but it gives you sort of a visualization of the curvature, how fast you're driving, how well can you follow a particular trajectory as you drive through campus. And that worked reasonably well. One of the things we then set up was that we set up a simple sort of finite state automaton of road following, crosswalk, following cars, intersection, designations. This is a simplified version. Today I think we have 25 different states in our finite state automata, but it's a very small set where for each of them you can have a different sort of control law for how would you actually execute this. You'll have a different set of how you rely on different sensors. If you're at a crosswalk, you're slowing down to sort of make sure that if somebody walks into the crosswalk, you can stop in time, and if there's nobody, you will continue. If there is a crosswalk, you will wait until it's free for about 2 seconds, and then you'll continue. Car following, you're basically staying. You don't want to do tailgating on people. They get very uncomfortable if you do that. So we'll do the car following, we'll stop, we'll do designations, we'll do intersections. Intersections, we maintain track of all the cars in the environment, and it's basically a first in, first out sort of system where everybody sort of has the opportunity to go first. And we wait for 3 seconds, which is, we've sort of learned this is actually a really bad idea. If you stop too long at an intersection, people can say, oh, he's not going to go anytime soon. And then, you know, they will try and get in front of you. So people are always sort of, there's very little tolerance for being a good driver. So that was important. So another thing we then slowly did was to build a better planning algorithm for this. So we started out, here's an example of a freeway intersection. We went away for COVID, and when we came back, there was a roundabout. So, you know, don't go away for too long because they will change the traffic structure. So for us, it was sort of important to figure out how can we build a system where even some of the very fundamental traffic laws. So we had never until after COVID had to deal with a roundabout. This was the first roundabout on campus. So suddenly we were like, what is this thing? So it was important for us actually to go in and do this. So we built a system where we took sort of traditional trajectory generation with a global plan, a scene representation, got it into sort of doing motion planning, where we're tracking things. So very traditional architect and said, what can we do to bring in the semantic information that we actually have so that we can do dynamic sort of trajectory generation? So we have a global plan here of what does it look like, how am I actually going to drive on campus. Then we overlay semantic information on this, which will tell us, are we driving over a crosswalk? Are we driving over a sidewalk? In some cases, you have to drive over a sidewalk to actually get to the next road. And we use this to contextualize how do you actually do the control. So we went from, sort of having the scene representation and a global plan to basically building sort of a conditional generator for how can I do it. So here you see, said when I come up to this intersection, I basically have 3 different ways I can go. I can turn left, I can turn right, I can go straight. We would then build in this so that we would have it. We would then go in, use sort of a standard autoencoder for modeling each of these. So you can basically model each of your hypotheses. You can now contextualize it into the semantic scene model. If you come up to an intersection saying you can turn left, you can turn right, or you can go straight, that's great. But if you don't know where the road surfaces are, you can't just say a straight is going straight across, because then it's a little bit of over. So it's important for us actually to be able to build in this into a model where I have my global plan, I have my local scene representation, I integrate this into a trajectory encoder, so I can now come out with a model where each of my trajectories are embedded into what is the specific layout. So this is all being computed on the fly on the vehicle, so that you get a dynamic scene representation, and you can take into account if something is blocked or if somebody's going somewhere else, you can actually do this on the fly. So we have sort of a data collection here where we drive around, and one of the things we did is, this is how a human driver would drive around. So we basically drove around on campus, got a set of data. Based on this, we would then have a data set that we could use for basically doing training of our underlying models, so that we could come up with something that was pretty good for this, and then plan out all of the different trajectories. It's a very, as you can see, it's not a full-scale model. It's only a 400 by 400. The egocentric map is sort of a simple 200 by 200 pixel map, so it's a very coarse representation of an overall area as you're driving through an environment. So we can then come up with a set of results where we can look at, depending on the length of the model, how well can you actually do fitting. And it turns out that overall, we can be, depending on the model you're using, we can be down to something like 25 centimeters, so a foot average accuracy. You can follow a trajectory, but you can do it at an accuracy that's sort of within a foot on this. If you apply a really coarse model, it will be about a meter, and it actually turns out that longer models doesn't really help, because you're not really, it's such a dynamic environment that doesn't really. So here is, let's see, is this playing? So here is basically how you drive around in these environments, and you can see it's actually, the red dot is where you're driving, and the green is sort of the prediction of where am I going to drive. And you can see it's a little, I don't know if you can see, there's not a lot of resolution, but it's staying sort of in the right lane. It's picking actually the right turning lane when it's turning or when it's going straight. So it has enough information from this and from OpenStreet Maps to do very good sort of trajectory following, to be able to go around these environments and do pretty good modeling. So we've done some fine tuning, but overall you can sort of see, so if you see it here, you can sort of see here is sort of a trajectory. This is what a nominal model would have done for a right turn. Here is the contextualized model, is sort of the blue. So you can actually see the green here would also sort of have gone actually in the wrong direction where with street maps, because we add sort of the contextual information. The blue actually corrects for it and says you should not drive halfway on the sidewalk and halfway on the street. You should do sort of correction based on contextual information. So that gave us sort of a really cool model for doing this. So we now have a system that actually can drive, and that's much more reliable on staying on the road. Yeah?
How often do you have to deal with objects that are not in your world of objects in the semantic?
Daily, I would say. People, we haven't had, but we see plastic bags, garbage bags, orange sort of traffic drums that were sort of, somebody put them there in the middle of the night. So a university campus is incredibly dynamic. So you have to have a reasonable balance between contextual information like the semantic street map and being able to react to, I have no idea what is the sane way of driving in this environment. And those cases will slow down, will be really slow speed, wait until we know we have enough time to be able to overtake and go around, or we'll stop and do an intervention. So one of the problems we have, some of the areas, we have these pillars that you have to drive through that sort of put up to make sure regular cars don't drive onto sort of pedestrian walkway. We have 2-3 inches to drive through those. In the beginning, I asked the students to always stop there because, otherwise I would have a car that sort of had a clean sight. So now the students drive through this. But often we would go really, really slow because these cars cost money. So one of the things that was, all of this was sort of done, if you look at it, on real data, driving on campus. I'm a strong believer in, if you can't do it in the real world, simulations are for people that can't do it in the real world. So that was that's one of the mantras that was you should really do it in simulation. The students repelled against me and said, you know what, we should really have a way of doing simulation before we do it in the real world, because he gets really upset when we run into something. So they built actually a 3D model of a third of campus as a digital twin. So what if you have a digital twin? You can use it to do early testing before you do it in the real world. But you can also do it to do basically post-mortem. If you ran a mission with raw specs, we can play it back in the simulator afterwards. So we built, it turns out that there's a really good tool in MATLAB called Roadrunner, which is designed to build 3D traffic informations. So if you have a campus license for MATLAB, you got it for free. And it can build sort of complete models with traffic signs, with roads, with everything. So the students went in and designed, basically took OpenStreet Maps and used this to generate a set of trajectories, put it into Roadmap, the Roadrunner, build a graphical model of this, which we then run in Unity. So we have a Unity model where we can do all of the traffic simulation. You can do a lot of the evaluation before you go in and run it in the real world. And then for some parts of campus, we actually have, so we have a system of Falco, Koster, and Dominic Meyer, where they use 16 drones to build 3D models of the environment. It was really designed to do what is called cultural heritage. So we're worried about some places in Syria, in Israel, Palestine, these places, there could easily be a war, and some of these cultural heritage moments could actually be torn down. So we built a team that flies around the world, builds 3D models, annotated 3D models of these structures so that we preserve them for prosperity, for longevity, so that we can guarantee even if there is a war, even if they're torn down, we have a digital representation of these. So, of course, our lab for that is to build a 3D model of campus. So we have very rich 3D models, so we've integrated those in to this. And if you don't have these are very nice models that we can get out of this. They're accurate. 5 centimeter accuracy is the 3D reconstruction for very large scale structures. For some of them, you could just also go in and do Google. So Google Maps will give you 3D models. You steal them from Google and put them into your representation. So for some of them, we can get 3D models because we have 16 drones that can fly around and do this. And for the rest, we use Google structures. So that now allows me to actually build a model. So here is the car driving around. Here is the digital twin model of driving around this. So you can see we still have work to be done on traffic poles and stuff like that. But basically, we can drive around here. Here is then ground truth, what the semantic model looked like. So now I can actually compare my semantic model to what ground truth looks like according to the Unity model. They can do it in a sports car like mine, and we can do it in a golf cart. But basically, this has been incredibly helpful for us to be able to build a 3D model that we can use to drive around and do early testing, to do early benchmarking. So if somebody comes up with a new control algorithm, they test it there before we test it on the golf cart. We do ground truth testing for our semantic mapping to guarantee sort of how well does it actually match up against this. And the fact that it's available in standard MATLAB sort of makes it very easy to do all sorts of cool projects. So I promised I would shut up before 3 o'clock, so I'm actually ahead of schedule. So for us, it was interesting to try and build this sort of autonomy for micromobility. And it was more because I really wanted to understand where are the hot problems. I haven't talked about this. I have sort of a separate representation about trying to do intent recognition of pedestrians. This is really hard. And there are pretty good models available that can predict the intent of a pedestrian 2 seconds into the future. It's very hard to find models that can predict 10 seconds into the future. You can't drive through an intersection in 2 seconds. I have a really good sports car. Even I can do it. So, you know, a golf cart is certainly not going to get through this in 2 seconds. So we have to figure out how can we come up with better models. Right now, we're also trying to understand how can we do contextual models for this. Can I understand the intent, but also how can I impact the intent? I'm always saying, you know, if I just do Italian driving, come up to the intersection, stop, sort of gas my car, drive around the corner. Everybody's going to stay at the side and sort of, that's Italian driving, but, you know, maybe that would not work on. So how can we actually, based on the driving behavior we have, how can we influence group dynamics? So for us, that's a very interesting problem we're trying to work on right now. How can we do this? At the same time, given that we're doing this in the real world, it's incredibly unforgiving. It's noisy, the lighting, you know, you have to be able to drive when the sun is just above the horizon. And that's just, you know, most of your sensors are just going to be fully saturated. You can't sort of park at the side of the road and say, well, I'll start again when the sun has set. So we need to figure out how do we build redundant systems that are very good at this. How can we make sure that the systems are truly dynamic? Because our campus, we've not driven a single day on campus where the map is accurate from one day to the next. Just to tell you how, you know, when people build HD maps and said this is a good solution, that's not true. So for us, it's an interesting design challenge of how do you build autonomous systems? How do you make them robust? And more from sort of the intelligent systems, trying to understand the context. So as I said before, sometimes there's a stop sign and there's road work next to each other. If you don't understand this, you are always going to be the sitting duck that's sort of parked at the side of the road while the rest of the world goes on. So we need to be able to build these. We need to solve these problems. So there's some good problems out there. So there's no shortness of problems to work on. We're not going to get to a problem where this is going to be fully autonomous, working 99.999% of the time anytime soon. So for me, that's sort of good news. At the same time, it's sort of because of all the possible problems, there's lots and lots of applications and lots of publications in there for this, which is very nice. So I'm happy to have a fantastic group of students that are actually doing this, and they keep going off and getting better jobs and get paid than me, which is a good problem to have. So I've been very fortunate, and I think that there's a lot of cool problems here. And with that, I'll say thank you. Questions?
With the finite state automata, when like a new context is discovered, I was kind of wondering, is there like a mechanism for possibly updating with new states of behavior if it's discovered?
So the way we do it today is that we basically do sort of a post-mortem. So we go back to the simulation system after a mission and figure out where are the interventions. And that was sort of like the earlier I showed you sort of an intervention map. And then we sort of used this to figure out and said, wait a minute, there's an area here where we need to be much better at doing intent recognition at intersections. So we basically do a post-mortem and do sort of machine learning on this to figure out, are there clusters of behaviors that could be addressed by a new finite state automata? So it's sort of standard machine learning on, can I do behavior recognition on it? More questions?
So you mentioned that you are using an Intel Xeon, that's a server-grade desktop.
top processor. The question I have is, how do we move towards like an SoC type of a solution that is low power? Because the vehicles we see today almost have all the sensors that we need for self-driving. We just need a solution on chip kind of a thing to help us with that. So how can we move to that?
So so the good news is we're getting very close to that. So if you look at it, Intel, Qualcomm, Huawei, all of them have sort of chip systems that are actually being designed for this. Apple has a chip for this. They just haven't told us yet that they have an autonomous driving car project. But so we're getting, so for instance, we worked with a Qualcomm. So Qualcomm has the 965, which can take input from 13 cameras. It has 8 GPUs on board, and it has 5 CPUs. And you can sort of selectively, so you can run 8 camera deep learning networks or whatever on these concurrently on a chip, and the chip, is cheap enough that you can have it in a cell phone. So we're working with them on some of that, and the board, the prototyping board, which is called RB5, is basically $500. So we're getting to a point where we get enough computing power. The hard part is they are not very easy to program, which is still a huge challenge. So, but also, and you need to find people. So I show you the camera that Dominique has developed with 32 cameras in it. All of that is programmed in an FPGA. Unless you have a Dominique Meyer, these are impossible to program. So it's an interesting challenge for us as a ECECS. How can we build hardware architectures that are also programmable? So, today it's hard to go from, I would like to get to where you tell me what the algorithm looks like and I can automatically compile it into hardware where you automatically optimize this. That's still going to take a time, some time before we're there. But we're seeing, I've driven in the Huawei car in Shenzhen where they drive around and there are no longer any traffic lights. So you go through an intersection like this and you pray a little bit before you go into the intersection, but it actually works. So we're seeing those. We're seeing Qualcomm is testing their Qualcomm Drive processor, and we know Intel is doing the same thing. So it's coming. But I don't think it's not the hardware that's the lacking. It's the IDE that allows me to take my algorithm and actually map it onto a piece of hardware.
That was the next question I was coming to. So we usually see software architecture built around ROS. So I just wanted to ask the viability of ROS, because ROS on like a low power system is kind of difficult to run because it needs a backend operating system to support. So,
sure.
Yeah.
That and so I think we're mainly using ROS because it's it has. So I'm from Denmark, so for me it's sort of the analogy to Lego. It has enough Lego bricks where I can do sort of rapid prototyping and build most of the house, and then I have a few blocks left where I can sort of put it in and actually get it very easily sort of installed. But the problem is that it doesn't run real time. And some of this has to be real time. It can't be, well, I was swapped out when we went through that intersection. It's not reliable. So we need better real-time systems. We need to see this mapping. So but there are AutoWare, AI. There's a number of these that are sort of building on ROS2 to get this. And in ROS2, you're getting better communication architectures. So the DDS is getting switched out. Some of it is in purely in memory. Some of it is shared memory. Some of it is sort of certified communication protocols. But at least for me as an autonomy researcher, I don't want to get buried into that because I feel this is going to be solved by very large corporations where I can't compete. Because I think the other problem I have, for instance, with things like autonomous driving, I don't want to get involved in autonomous driving on the highway because Intel, TuSimple, Waymo, Aurora are beating me. and you know, they have 900 million to spend on an R&D budget. I have 6 or 10 PhD students, so I can't compete in that space. So I need to be able to find what I call white spaces, where it's very unlikely they're actually going to work on this anytime soon. There I can do my R&D, and then hopefully they will adopt it. So I think for us, we need to think about where are the white spaces I can be working on long enough to get my thesis out before the big guys overtake me.
Like, for example, rain and snow. Have you tested this when it's raining?
We've tested it when it rains. We've not tested it in snow. San Diego doesn't know about snow. So that's one of our big challenges, actually, that I'm saying that there's a lot of these systems that are being tested under unrealistic conditions. But because, you know, they make assumption that it's sunny every day. Well, I used to live in Stockholm, where it's sunny 3 days a year, you know, so it's not quite realistic.
I wanted to ask, has there been any situation during your experiments where the system didn't know what to do and you will have to resort to some form of reasoning in order to decide how to move?
Oh yeah, lots of them. But for the early systems, we resorted to basically doing an intervention. Like, you know, where you see the road work, where there's a stop sign and there's things on the side. The system is not smart enough, or there's a guy standing there and said, you can go. And the system is, you know, not interpreting hand gestures from, and knowing, you know, is this a pedestrian? Is this a traffic guide? Is this a police officer? So there's lots of cases where we need to get, you can't just use what I would call a simple sort of lookup table approach to actually doing this. You need to have real reasoning. And that's what's missing today.
If there's a truck in front that carries stop signs, and the car is coming, the autonomous car is coming from behind and sees those stop signs,
it would stop.
is it smart enough to realize that
Today,
the
no.
stop sign is moving?
No. Today, not. And that's where I think there's a lot of these cases where we getting that sort of what I call contextual knowledge is incredibly important. And most of these systems fail today because we don't have a deep enough semantic model that we actually understand what is stationary, what is moving, what should I take into account. So, you know, if it's stop signs, normally I should take them into account. Wait a minute, they have a moving reference frame, so I can probably ignore them. All of that is just not in the systems today.
You know, there was recently, I read in the news that there was a truck that was carrying traffic lights, and the autonomous car going behind would see red.
Right. But the same, there was less than a month ago, there was a story in, I think it was New York Times, where Tesla has a particular place in Yellowstone Park. If you drive in autonomous mode, across that intersection, they will always go off the cliff. So it'll look like a highway or something like that, and said, okay, we can go full speed here, and then, you know, did I have 5 cases of that? This is scary, and that scares me that these systems are not being, we're being, you know, we're not at 99.99, and until then, it's going to be tough.
Do you think you can achieve that in next one?
Sorry?
Do you think you can achieve that in your lifetime?
Yes, I think, but I'm going to say something that's politically incorrect. We're still recording, though. But basically, I think people are so enthused about the straight line to the target that we're doing sort of deep learning models and stuff like that, and making the assumption that that's actually going to make it. And I'm fundamentally disagree with that. Unless we build in cognitive processes on top of this, where you really get sort of the contextual awareness, you can reason about it. It has to be a combination of basic perception, semantic modeling, situation awareness, reasoning that gets us there. Right now, we've only taken the bottom level. So we need to get those other levels. I think, it's like, Elon Musk said, we will have autonomous driving taxis before the end of 2020. didn't happen because we sort of realized this is a little bit harder than we thought initially. And I think most of these companies is going to get to the point where they recognize that it's actually harder than you thought initially. That doesn't imply that we can't do. So we're seeing companies like Too Simple that are driving coast to coast on the interstate. And they're saying that you can do this if there are no traffic work on I-40 that day. They can drive without interventions from North Carolina to LA. But if there's traffic work, they're in trouble. And I think we will get to this where we can relieve the driver, but we're not going to get to full autonomy anytime soon until we get a new paradigm that is not what I call a self-parameterized lookup table. That's just not going to cut it.
That's a real question, because
Yeah.
everybody thinks about machine learning and AI. The kind of AI we need, we don't have it yet.
Exactly. No, we don't. But at the same time, we shouldn't sort of throw out the AI today. But I think it's very important that people should be honest about where are the limitations, rather than saying we've now solved autonomous driving, because that's being sort of sales. That's sales rather than science.
Do you think we're going to have fully deployed self-driving cars in our lifetime?
Yes. That I believe. So I hope to live long enough. So.
2061, we'll bring Yanis and Henrik back here, record the question and double check who was right. You gave 105 years ago, let's bring in 2061, Yanis and Henrik.
Yeah. No. So, but I think you have to remember it's an exponential curve, and I think we will sort of get to a bifurcation in AI, where some people will continue to insist that if we just do sort of basic training without sort of what I don't think of smart and not with enough semantics, I don't think that's going to get it. But I think there's another bifurcation where we will see people that will say, you know what, we really need a new paradigm. And once that happens, I think it will go fast. Okay.
I want to thank Dr. Christensen for this wonderful talk.